Hi, everybody. Good afternoon. It's a great pleasure to me to introduce Professor Hugo Proença, Departamento de Informática, Universidade da Beira Interior, Portugal. He was an associate professor until September this year, and now he's a full professor. The first time I met Hugo was on SIBGRAPI 2018. On that occasion, he was the presenter of a tutorial about biometrics. Nonetheless, we already knew him from dozen papers published about biometrics on top IEEE transactions, such as pattern analysis and machine intelligence, and information forensics and security. We highlight some activities. He was the coordinator. He was coordinating the editor of the IEEE Biometrics Council newsletter and the editor of the IEEE Biometrics Companion Journal about ocular biometrics. He also serves as a member of the editorial boards of important journals on computer vision and biometrics. Well, now we are going to watch the talk of Professor Hugo Proença entitled Advanced in Visually Interpretable Biometric Recognition. Folks, you can submit the questions on YouTube and also on the Discord channel. Hugo, thank you in advance. Now it's with you.
Thank you very much, David. So, hello everybody. Good afternoon. Boa tarde aí para os brasileiros. So, my name is Hugo Proença. I'm talking from the University of Beira Interior at Covilhã. It is a city in the interior part of Portugal. We are nearby the Spanish border. So it is really a pleasure for me to provide you this presentation. Many thanks for the invitation. My idea for today is not only to show you some basic concepts about biometric recognition, but most importantly about machine learning interpretability. Okay, I will show you the most classical existing techniques for image interpretability. I will show or will try to emphasize their weaknesses, and then I will present a solution that we've been developing in our lab for providing a visually interpretable representation of the responses given by a biometric recognition system. In our case, working in the verification mode. So here you can see the summary or a summary of the presentation I have prepared you for today. We will start by briefly overview some concepts about biometric recognition, the traits that are the most typically used in this domain. Then I will summarize the classical techniques for machine learning interpretability or explainability, and also we'll try to provide you a short taxonomy of the existing approaches. And next, we will enter in the main part of the presentation, where I will show you our partially, at least I would say, self-supervised approach that we've been developing in our group. Essentially to explain why a pairwise biometric recognition system reports a genuine or an imposter comparison. My idea is to show you not only the main stages of the proposed pipeline, but also to discuss the rationale behind each choice. Now, with respect to the first part of the presentation, biometrics is the main scope of this presentation. I am assuming that everybody or almost everybody knows what it means. Essentially, it refers to the automatic recognition of human beings based in physiological or behavioral features extracted from the human bodies. So there are many different ways to perform biometric recognition these days, from the classical fingerprint, iris, face traits, up to other not so common possibilities as the DNA, sclera patterns, vascular structure, gait, and even other really, I would say even a bit strange traits that were proposed recently. Among one of the most strange, I would say, traits that I heard was the sound of gait. Okay, not the gait, not trying to recognize someone based on images or videos of the way a person walks, but exclusively analyze the sound of gait, the sound that somebody produces when walking at a specific part or a specific region of one floor. Well, I would say it's quite strange. I'm not sure even if it is minimally useful, but and anyway, I think that it is accepted, I would say, by almost everybody that biometric recognition technologies represent a particularly successful case of pattern recognition. Okay, and by this type of systems, they are deployed all over the world for many different applications. And I would even say that biometric recognition systems are perhaps the type of automated agents that interact with the largest number of human beings all over the world. Among all automatic or all automated technologies or agents, I would say that biometric recognition is perhaps the topic that interacts with the largest number of human beings. So that's why I think biometric recognition is really a crowded topic in research and represents a particularly successful case of machine learning and pattern recognition domains. Okay, so as I told you, biometric recognition systems, they are deployed for many different applications, and they have really good, or I almost say remarkable effectiveness. So, and beside this, recently, as in many other computer vision applications, methods that are based in deep learning frameworks, they also have been consistently advancing the state-of-the-art performance. So it is known that this kind of models is extremely sensitive to the amount of learning data used in the training phase. And upon the availability of sufficient amounts of data, which in some cases it can demand millions or dozens of millions of labeled instances, this kind of frameworks attain really low error rates. Also, one of the main features, perhaps the major feature of this kind of models, is their ability to autonomously extract the most discriminating features between the classes that are being handled in a particular system. And then, apart the enormous cardinality of such feature sets, a major difficulty is to establish some evident correspondence between the features that are extracted, that are being analyzed by the system, which in practice they are determined by the shape of the filters tuned in the convolutional layers, and the semantic components of the data that is being analyzed. So as main result, in practice, this kind of frameworks is almost always seen and used in the black box paradigm. So the responses are deemed to be accurate, okay? But we do not pay too much attention to the interpretation of the system inner state or to obtain a human understandable explanation behind a decision. And that's perhaps, this is perhaps the main motivation for the work we've been developing in our lab recently, and also the main motivation for the topic I'm talking about today. Okay, so let's move briefly to the second part. I will try to keep as brief as possible the first part and the second part of the presentation, to give a bit more space for the main part, where I will explain you our solution. So regarding machine learning interpretability or explainability, My idea, as I told you a few minutes ago, is not only to overview the most classical techniques that were proposed, but also to highlight their difficulties in obtaining actual human understandable representations for a response, for any kind of response, and in particular for the responses provided by systems that receive pairs of instances, and that actually one instance is composed by pairs of images, as a biometric recognizer does when it's working on the verification mode. Okay, one important thing. You might have noticed that I've been using simultaneously the terms interpretability and explainability. What's the difference between both terms? At the bottom line, they seem to be complementary concepts, and I would say that they distinguish between each other mostly by the perspective that they have to a specific problem. Interpreting essentially involves to be aware of the meaning of something, to be aware of the inner state of a complex system. This is kind of almost a passive perspective, but in opposition, explainability seems to be a bit more demanding in the sense that it is supposed to explain the meaning to someone understand a specific concept. In this perspective, I think that explaining something implies that we previously and already interpreted it. So interpreted it is related with understanding the inner state of a system. Explaining it evolves to be to provide a list of features, a list of reasons for the interpretation that we previously did. Anyway, I think that there is an obvious relation between both concepts. I would even say that I'm not completely sure or certain if the method that we've been developing is actually falls in the scope of interpretability or explainability. I would say that in some sense it's in the border between both. Both interpretability and explainability, they are everybody agrees, or everybody tends to agree that they are evidently valuable in general pattern recognition problems, and in particular for biometric recognition. For instance, for legal or security purposes, typically, not only we are interested in obtaining an identification, a positive recognition from a system, but it is also useful, and in some cases it is mandatory, to have a set of reasons that justify or support a specific response. And this is really important. This set of reasons is important, is mandatory to be used, for instance, in forensic domains. Interpretability, or the ability to perceive the inner workings of a model, is also useful for transfer of knowledge between similar domains. Also, it contributes to increase the confidence of users of a recognition system, and it even contributes to additional protection against unwanted bias. Okay, so there are many reasons that we can present to justify the interest and the growing interest that the research community had recently in the interpretability and explainability concepts. And I think that there are even more reasons in the specific field of biometric recognition. As I told you, perhaps the most evident reason is to use the responses of a biometric recognition system for forensic or security purposes. Okay, then regarding machine learning interpretability in the specific case of biometric recognition. There is also one additional problem, one additional level of complexity that evolves the type of data that we are handling in biometric recognition. Typically, we use multimedia streams, either images, videos, or sound. But the thing is that most of all the classical interpretability, explainability techniques, they were proposed, they were designed for tabular data. Okay, for tabular data where we have a relatively short number of features, but even more important than that, where such features have in an independent way a human understandable semantics. Okay, so where we can understand the meaning, the notion behind a single feature. When we are working with multimedia data, it is not realistic to consider a pixel or a voxel as a feature, as they do not constitute any semantic consistent entities. And also, besides this, the cardinality of such feature set, the number of pixels or the number of voxels in streams, completely forbids its use in a way similar to what we do for tabular features. Okay, here in this slide I am showing you one of the most classical techniques for interpretability, Shapley codes. Okay, I am showing you a Shapley plot that interprets or explains a specific response that or a model that predicted the chances of survival for one specific Titanic passenger. Okay, you can see that in this case an output value, the probability of survival of 0.93, it was produced, it was the output of the system, and in this case, three features were considered the most important, as you can see here by the Shapley plot. The fact that the passenger was not in the third class, class 3 equals 0 or class 3 equal false, increases the chances substantially, increases the score substantially. Also, the fact that the passenger was a female also increases the survival chances even more in this case, as you can see by the amplitude of this part of the bar. And finally, in opposition, the fact that the passenger was not on the first class slightly decreases the probability of survival. So, in summary, using the classical techniques such as this one, exactly as it was proposed for multimedia data, it's in practice it is impossible. If I have to summarize or to provide you a simple, well, a really simple taxonomy for the interpretability and explainability solutions, I would say that we can divide the existing techniques according to three properties. Okay, so we will have depth, we will have scope, and we have the applicability. Depth discriminates between the approaches that in some way they constrain the model complexity. For instance, typically by trying to emulate the system responses with a simpler system, or others that create other family of models that are naturally interpretable. Okay, there are also other types of techniques that are created only after the system learning phase and exclusively attempt to analyze the system outputs, without concerning about the inner state and the actual complexity of the system. These are the post hoc explainability techniques, while the first ones that I talked about that constrain in some way the modal complexity, they are designated as intrinsic explainability techniques. Then, with respect to the scope, scope determines whether the techniques aim at explaining an individual response, only one response provided by the system with respect to one instance, okay, associated to a single instance, or on the other way, if they aim to explain the whole modal behavior in a cohesive way. The latter are designated as global methods, while the former are designated as local techniques. And then we have the concept of applicability. Applicability divides the techniques depending whether they can be used in any kind of machine learning model. These are the modal agnostic techniques, or others that can be used or associated only to a particular kind of model, which are the model-specific techniques. In the next slide, my idea is to provide you perhaps the three most typical techniques I would say seen in the literature. So we have Lime, we have Shapley values, and we have Saliency Maps. Saliency Maps have been augmenting their popularity recently. So starting by Lime. Lime is a family of modal agnostic, local, and post hoc models that typically use a surrogate simple model, almost always a linear model that is trained on perturbed versions of the input data. I will show you an example in the next slides, and tries to approximate the responses provided by the original system. Okay, and then upon learning, Lime has a learning phase, but when we use a linear system as the simpler model, learning exclusively implies to solve a system of linear equations. Upon learning, the set of weights obtained for each token, for each part of the input, provides the interpretation or provides the explanation for that particular decision. The tokens that have or that receive the largest weights in magnitude are believed to be the most important, or the ones that most evidently contributed for a particular response. Okay, so then we have Shapley values. Shapley values are the kind of plots that I showed you a few slides ago. They are based in game theory, okay, and have several points in common with Lime. The idea here, and again, is to explain a particular feature for a single response, okay? Both are local models, but in this case, without constraining the model complexity, okay? It is a model agnostic and it is a post hoc technique. The idea is to create several combinations of feature and of feature values that are named coalitions. Okay, we have multiple coalitions, and we divide the existing coalitions into two groups. One group where the feature of interest has a specific value, and the other group where the feature of interest, the feature that we are analyzing, does not have that specific value. And then we feed both subsets to the system and get the responses that the system returns us. We measure the differences that are returned by the system for both cases, okay, and the accumulated differences between the responses provided for the first subset and the second subset. Those accumulated differences will approximate the importance of the feature that is being analyzed in the final response. Then we have more recently Saliency Maps that have been really augmenting and becoming highly popular, in particular for deep learning frameworks. Okay, the idea of Saliency Maps is quite straightforward. I would say that they simply obtain using a learning algorithm. They simply calculate the derivative or the gradient of the responses provided by a network, not with respect to the system parameters, to the weights, but with respect to the positioning of the input data. Okay, and by obtaining or by approximating the derivative of the responses with respect to the input data, they determine which pixels, or actually which regions, which super pixels were the most important for an observed responses. I would say that these three, if somebody wants to start learning about explainability or interpretability, I would say that these three techniques are perhaps the ones that should be studied first. There are other techniques such as partial dependence plots and accumulated local effect plots, but in this case they are only suitable for a completely orthogonal analysis, okay, in the sense that they correlate one independent input variable to the observed target. And also this family of methods is also exclusively suitable for tabular data, considering the number of features that it is realistic to analyze. Now, in the next slide or slides, I will show you three examples, one for each of the techniques that we discussed with a brief, more detailed line, Shapley values and saliency maps. Okay, so starting by line. So it is a local model, as I told you, that using a simple linear model tries to reproduce or replicate the responses provided by a complex model, a complex network. The idea is, I would say it's really an intuitive idea. We define or we identify a set of superpixels in the images, regions that are semantically consistent in the image, and then we iteratively perturb. And when I say perturb, I can say simply we mask out some of the regions in the input data, okay, and evaluate the responses provided by the system that is going to be interpreted. Okay, and then by solving a system of linear equations, we obtain the weights associated for each region or for each superpixel, where the regions or the superpixels that receive the largest weights in magnitude are considered the most important for a particular response. In the example you can see here, given at the right part of the slide, you can see the input instance, okay, and the explanation provided for the class Labrador, okay. In this case, the pixels that are non-masked, the non-gray pixels, were the ones that got the maximum coefficients in the system of linear equation that was solved. Of course, that these regions are completely dependent of the class that is being explained and of the system that is being explained, and the regions will be obviously different for explaining any other class. Regarding Shapley values, these ones, even more evidently than in the case of Lime, I would say that this type of plots or values are even more evidently only suitable for tabular data, even though there are different variants that were proposed or that have been proposed for adapting this kind of maps or values to multimedia streams. So the idea, as I told you here, is to start by identifying one semantic coherent feature and perceive if a particular value for that feature was or was not important in the response that we observe. To do this, we create iteratively many coalitions, starting from 0 constant up to n constant feature values. The features that are not in the coalition, we draw random values for those features, and we start creating the two subsets of instances that I talked to you a few minutes ago. Once we have the two subsets of instances, each one with the different combinations of features, but where in one of the subset, the feature of interest always has a specific value, while in the other one, the feature of interest never has that specific value, then we get the responses from the system, and we accumulate the responses provided for the first subset and for the second subset. Intuitively, if the feature value that is being analyzed is not important, the responses will be quite similar. But in opposition, if that feature value, if a specific feature value for that particular feature was really important for the response of the system, the difference, the accumulated differences between the responses will be large in terms of magnitude. And so this one is considered one of the, well, it is undoubtedly one of the most popular. Also, it is particularly expensive from the computational perspective. Okay, but I would say that if you have tabular data and not an enormous number of features, this is perhaps the first technique to be used or to be tested. Then we have Saliency Maps. As I told you, they are naturally suitable for deep learning complex frameworks. They simply evaluate using retropropagation or a similar algorithm. They evaluate the derivatives of the scores, but with respect to superpixels in the image data, and values or regions with the largest derivatives are considered the most salient, or the most important, or the regions that most evidently contributed for a particular decision of the system. In practice, this type of saliency maps are actually foreground analyzers. Okay, they are kind of foreground detectors that also, and this might be a problem in certain circumstances or certain problems, they tend to focus on individual instances of the input data when we have more than one instance of a particular object in the scene. And this can be, for some cases, depending on the application, this can be a problem. And finally, in this slide, I am showing you the results that are typically attained by these three techniques: line, Shapley values, and saliency maps. For our purposes and for the purposes of our work, we were particularly interested in perceiving how intuitive are the explanations produced by those techniques on pairwise recognition and on for a pairwise biometric recognition problem. Here, I am showing you two comparisons, okay, two imposter comparisons. Actually, these imposter comparisons, they were correctly classified by the system. So we are trying to perceive why, or the reasons why these images A and B were not considered from the same person. And as you can see by the results provided in the right part here under the explanation column, I'd say that the interpretations or the visual representations, they are far from visually pleasant. Okay, they are far, and they are hard to interpret. And I would even say that the problem is particularly evident for the case of saliency maps. Saliency maps hardly can be considered as providing an intuitive explanation for the response obtained, or in this case, for the imposter decision that was obtained. So this was our main motivation. The existing techniques, even when adapted to multimedia data, they produce explanations that we do not consider to be actually understandable. That this provides us the basis for our subsequent work. My idea now is to move to the most important part of the presentation. I will try to provide you the details behind the solution that we've been developing. Okay, let me clearly state our problem. This slide illustrates the way we framed our problem. Note that we consider that one instance is composed of two images. In our case, and as a proof of concept, I would say, because the method that we've developed works, we use the periocular region as a proof of concept, but the method would work in an exactly equal way for any other type of traits, for face, for iris, or for any other or almost other biometric trait. So we also assume a biometric verification setting in the sense that, as you perhaps might know, when a recognition system is working in the verification setting, the task is simply to decide whether the pair of images is from the same subject or not, if it is a genuine or an imposter comparison. We consider a genuine comparison when both images are from the same subject, or otherwise an imposter comparison when images are not from the same subject. So at the end, we have a binary classification problem, and this is an evident case. This type of applications is an evident case where deep learning classification frameworks, they achieve really good performance, okay? But the problem, as I told you, is that they do not provide any clue about the features that justify a specific response. So, and here, in this slide, I am trying to provide the big picture of our solution. I would say so, as I told you, we have one input instance composed of two images, and our processing chain can be decomposed into four main tasks. So we use a state-of-the-art semantic segmentation model that will discriminate between 8 different potential biological regions in the periocular region, and then we use autoencoders that are responsible to obtain multiple versions, and I will explain you those versions of latent representations of the input data. So this means that using the mask-R-CNN results, we are able to create different versions of our input data, and using autoencoders, then we get multiple latent representations for our image. The idea is that such latent representations should be semantically coherent in terms of any features, or in terms of the major or main features in the periocular region, and then the main learning phase uses a generative adversarial scheme to create at the end different versions of the input data that will attenuate the differences in phase between the samples that are being matched. Okay, this is the main idea of the GAN phase near the end of the learning phase. Our goal is to attenuate the differences in phase between the images that are being compared. And when we are able to attenuate those differences in phase, in practice, when we align image A and image B, we can even compare point by point, pixel by pixel, the values that we have at each position. And any difference on those representations that are in phase, one against each other, any difference will actually correspond to biological differences between the subjects and not be determined by differences in the pose or differences in lighting or any other kind of difference. At the end, the final goal is illustrated here in the right part of the slide. We should obtain a representation of the input data where the regions that were considered the most important to sustain a particular decision should be highlighted. Okay? In this case, we will use the level of red as signal to emphasize how much important it was a specific position in the input data to sustain or to explain a particular decision. Okay, so as I told you, everything starts by the semantic segmentation phase. Here we use, I would say, a relatively short set of learning samples that were manually labeled at the pixel level. Okay, we feed a well-known model. There's nothing new here. We simply feed a mask RCNN network in order to obtain a segmentation mask with 8 different regions, let's say with 8 different intensities at the pixel level, representing the iris, sclera, eyelids, eyebrows, skin, hair, glasses, and background. So our idea is to have, in some way, information about which biological or not biological component is at each position of our periocular region. It is important to stress that this is the unique case of the proposal of all the pipeline that is fully supervised. Okay? Even in this case, considering that we are working at the pixel level, we are not dependent of a too large number of annotated learning samples. We observed that using some dozens, large dozens, perhaps a few hundred images, we can obtain acceptable, even good results can be obtained, as you can see by the images given in the bottom part of the slide. So, to summarize, recall that at this first point or this first phase, we simply use a state-of-the-art segmentation network to obtain precise information about the localization of the main components that likely appear in a periocular sample. And now, in the next step, this part is particularly important because this step that I am explaining you here is the one that justifies the way we call to our approach, or we consider our approach as self-supervised, because now we will estimate the labels that will be used in the main learning phase. The idea here in this part is to encode, to obtain latent representations of the piecewise components in the periocular image. As we have a segmentation mask, we are able to obtain, starting from the original data, we are able to obtain 8 different versions of that data, where each version only contains one component and mask out, in practice we set to 0, all the remaining information. So this means that starting from the input data, we create one iris image, and then one sclera image, The iris image only has the information about the iris, and everything else is black, is zero. And the same thing for the remaining biological components. And simply we use autoencoders. We consider those 8 versions of the input of our input data. We consider those 8 versions as input of our autoencoder, and the idea is to obtain a compact representation of the main features of each component. Okay, this compact representation has around 4,096 coefficients. In practice, we can say that using a vector of 4,096 coefficients, we keep the most important information about the iris, and then about the sclera, and then about the skin, and then about the glasses, and so on for all coefficients. In the next step, we use a low dimensional manifold. Okay, we project this set or these vectors into a low dimensional manifold that will be used, which coordinates will be used as labels in our main learning phase. Okay, the rule with this representation, and here we use different manifold learning techniques. We use T, S, and E. We use mainly UMAP, and the idea was for all components to project the corresponding codes into a bi-dimensional manifold. Okay, where in practice each image will be represented by 2 coordinates. Okay, as you can see here in the example given at the right part of the slide. And our idea, and we verified that this can be easily obtained, is that the regions where a specific image is projected to has an obvious relation with some obvious semantical feature corresponding to that part of the periocular region. For instance, if you analyze the manifold given, or the plot given here at the bottom right part of the slide, you can see points represented in 4 different colors. So we have black points, blue points, red and yellow points. Black points here, they correspond to really heavily pigmented iris, black or really dark brown irises. And then in opposition, you can see the blue region, and the blue region correspond to blue or light green irises. And then we have the intermediate values. We have brown, a bit more dark or light brown irises that are placed in the middle or in the central part of the manifold. But this is perhaps the core, or one of the cores of our solution, because the idea is to, for one image, to obtain 2 coefficients that in some sense they represent a human understandable property of the periocular region. We will have 2 coordinates for the iris, 2 coordinates for the sclera, and so on for the 8 coefficients. And these coordinates will be used here in the next part. In the next step, we use the manifold coordinates that we get for each region, and we simply train a CNN regressor model. This CNN, it's a simple convolutional neural network that receives, in this case, not the masked versions that the manifold projection techniques receive, but the full periocular sample. Okay, we will train this convolutional neural network to receive a full periocular sample, and depending on the coordinates that we obtained in the previous phase, we want that this regression network is able to estimate at once, in a single shot, the iris coordinate, the iris coordinates, the sclera coordinates, and so on for all the coefficients. Okay, and this network will also be important because it will be used in the loss formulation of the final GAN learning process. Recall, just to summarize that up to this moment, we have a way to use or to receive a full periocular region, and using a simple convolutional neural network to obtain 8 vectors, each vector with 2 coefficients, and each vector corresponds to a semantical property, an obvious semantical property of the input data. And this, I would say, concludes one important part of our method. The second important part is the way we will enforce that the latent representations that are obtained for the full image, okay, when we use the full image as input, should be disentangled in the sense that we want to enforce that specific regions of that latent representations only regard specific coefficients or specific biological components in the periocular regions. And this is what we do here. Okay, so in the exact same way, let me go back here briefly. In the exact same way as we do here in this slide, we use as input the masked version of the input, where only one component is highlighted at each time. This time we are using the full periocular region, and using the encoder part of the autoencoder, we obtain the same latent representation with 4,096 coefficients. But the idea is that now we want to enforce that, for instance, the first block should only contain information about the iris, the second block should only contain information about the sclera, and so on for the 8 biological components, or the components that we identified. And apart these 8 components, we also create one block, or we also define one block to keep the everything else information. Okay, by everything else information, I mean by exclusion of parts that the network, during the learning process, it should learn to encapsulate here in the final block all the information that is not being encapsulated in the remaining blocks. And as the remaining blocks cover the whole periocular region, the idea is that this block should encapsulate information about pulse and about lighting. We see this, or we regard this in some way as a acknowledged distillation strategy. How do we enforce that the first block only regards the iris? This is done in an implicit way, okay, by swapping blocks between latent codes. So at this point, during the learning process, the main learning process, we use pairs of images. For each input image, we obtain its latent representation, as you can see here, and then we swap codes of both latent representations. In this example, as you can see here, this swapped code contains, let's suppose that the first block is the one that regards the iris, contains the iris information of this subject and all the remaining information of the subject A. Then we use this swapped latent code, we feed the generator or the decoder module, we will obtain an image, and we will enforce, and that's where the previously learned convolutional neural network, the regression convolutional neural network comes into the game. We will enforce in this case that the iris coordinates should be the same of image B, and all the remaining coordinates should be the same as they were for subject A. Recall that using the manifold learning and then this CNN model, we are able to get the iris and sclera and all the 8 coordinates for each image. And during the learning phase, we enforce, supposing that the swap was done as it is illustrated in this slide, we enforce that the iris representation that is here in this image should be the same as it was here, and all the remaining representation should be the same as they were here for image B. And iteratively, by randomly swapping different blocks between images, the network naturally learns to encapsulate the iris information in the first block, the sclera information in the second block, and so on, up to the final block, where it will encapsulate all the information that is not being encapsulated in the remaining blocks. Okay, regarding the division of the blocks, of the latent code into blocks, we considered a particularly, I would say, interesting division. Some of the blocks, as you can see, they regard information that is evidently ID sensitive, for instance, iris, eyebrows, eyelashes, skin. Other blocks, they evidently do not regard ID important information. Glasses are not important to establish an ID. Background and also the blank, pose and lighting, is not important. Then we have the case of air. Air, it is considered a soft biometric trait, a soft biometric cue, but of course it can be easily forgeable, and so in SVR we did not consider it a reliable biometric cue. So at the bottom level, we divided our blocks into ID relevant and ID irrelevant. And here you can see the main or a cohesive perspective of our main graph of our learning model. So it's quite similar to the example I provided you in the previous slide. So we use a pair of images, we encode, we obtain the latent representations, we swap randomly different parts of their codes, and we reconstruct the images. Then, using an adversarial paradigm, we have a discriminator here that is responsible only to distinguish between images that were generated or reconstructed from swapped versions of latent codes, and images that were reconstructed from non-swapped versions of latent codes. But in this slide is actually the core of everything. The final idea, the final goal is to obtain this kind of representation in the image here at the bottom right part. You can see that this representation can be seen as how would subject A, you can see that there are several features of subject A here, look where with the non-ID features from subject B. What do I mean with non-ID features of subject B? We can understand this representation as how would subject A look if it is imaged exactly as it was subject B. So in practice, this image is an image of subject A aligned to subject B. And this kind of representation actually is not this exact representation, but it is in practice almost this representation will be matched against the subject B, and any differences between this representation will actually correspond to differences in to biological differences. Okay, so these are simply the losses that we use in our main learning phase. We use the reconstruction loss, we use the perceptual loss, the structural similarity measure between the reconstructed versions of the images, swapped and non-swapped. And this is particularly important, the mapping loss, because using the previously learned CNN regressor, that's where we enforce that depending of different regions that we swap here, the coordinates should change here accordingly. Then in inference time, the process is really simple. We simply receive pairs of images, swap codes, and obtain the reconstructed versions. You can see here that here we have an image, in the bottom part, we have an image of subject A imaged as if it was subject B, and the opposite here, an image of subject B imaged as if it was subject A. These two explanations will be used for obtaining the visual representations of the most important regions. You can see some examples here. Or you have subject A that is providing the ID relevant features, image B that is provided the non-ID relevant features. Okay, and you can see the result here. The result in practice is an image of subject A aligned with subject with image B. This is the main result. And finally, I'm providing you some examples of our inference results. For instance, supposing that we are comparing a black skin and a white skin person. Of course, that everybody says, okay, we can immediately perceive that subject A is not the same person of subject B. Here you can see the reconstructed version, the difference maps, but I would call your attention in particular to the explanation, to the final explanation. And the final explanation, we are illustrating by the level of red, there is a direct correspondence by the level of red at each position and how much it was that region important to sustain an imposter decision. So without surprise here, you can see that the skin was evidently the most important feature. Okay, and if you remember the justifications that we were obtaining for the other techniques for LIME, Shapley codes, and Saliency Maps, these are dramatically different, and in my view, they are much more intuitive. You can see here that the most important feature that justified why subject A and B are different are actually the skin, and also you can see that the color of the iris here is slightly lighter in subject B than in subject A. So you can see here, if you look carefully, you can see here that also the iris region has some level of red, indicating that the color of the iris is not the same between both subjects. You can see here another example, in this case of two white-skinned persons. If we once again analyze carefully the explanation, you can see that the outer part of eyebrows were considered evidently different between subjects, and if you look for the original samples, the shape of eyebrows is obviously different, and also the shape of the zygomatic and of the nasal bones were also considered different. The shape of the bones around the eye, they are also different between subjects. In this case, the color of the skin was only slightly important for the imposter decision. Finally, just for contextualization, I'm showing you an explanation produced for an art genuine comparison. You can see an example of two images taken under evidently different poses of the same person, okay, with a facial expression here in the image below that had significantly changed the shape of eyebrows. You can see the final explanation that we get, where the shape of eyebrows is slightly highlighted, but anyway, in a much smaller way than for the previous imposter comparisons. Okay, so I think that our time is already over. We are almost done. Let me just simply summarize our what we talked about. Recall that we started by showing you the difficulties faced by the most well-known interpretability, explainability techniques to handle biometric data, in particular pairwise image data. And then we described a processing chain to provide a more visually understandable model for interpretability or explainability. At the end, we have a post-hoc local model for pairwise biometric recognition explainability. Okay, so I think I'm done. This concludes my presentation. I hope that I have provided you a clear idea in some way behind not only the challenges in pairwise recognition interpretability, but also the rationale behind our processing chain. If you have doubts or any other question, I'll be happy to answer, okay? Thank you. Thank you.
Well, thank you for the very interesting presentation. I loved the subject. I hope the other guys also love it. Well, we have some questions here. Let's start. I will try to follow the order that they were present in because they changed the way. Well, let's the first one from Diogo Miller. Can sharp plots be generated automatically? Also, can they analyze the importance groups of features? I'm dealing with a problem that a single feature does not mean much, but the relation does.
Yeah. So I think that the answer to the first question is obviously yes. Okay, Shapley plots can be generated in an automated way, but one of the main features of Shapley plots is that they also only provide an orthogonal analysis, in the sense that we can perceive the importance of feature A, but we are not able to perceive the importance of feature A when aligned to different values of different features. So the idea is to perform only an orthogonal analysis. So I would say no for the second question. Okay,
thank you, Hugo. If we have a follow-up question, I will back on that later, okay? Let's move for the next question. Well, Diego Rafael Lúcio is a PhD of mine. Good afternoon, Professor. I'm trying to use the present approach in a pix-to-pix scan to segment the periocular region components, iris and sclera. We are using only 2 components. Have you any suggestion to me? For me?
Well, it depends. I think it depends of two things. It depends of the type of data, of the heterogeneity of the type of data that you are aiming to deal with. But I think that if you want to deal with data acquired in relatively constrained condition, relatively good quality data, you will not need too many images to obtain good results, not even with pix-to-pix, but with more classical semantic segmentation methods. Even using some, I'd say, around 100 samples, it can be enough to obtain good results to segment, in this case, the iris and sclera. Pix-to-pix, perhaps I would say that it would demand more data. If you have more data available, you would obtain perhaps better results, of course, but it depends on the amount of data you have and the quality of the images you are aiming to deal with.
The complexity of the problem, and it's a trade-off. Okay. He also complemented with that. I'm using the Saliency Maps before the gradient descended, and the output of it is used to update the network's weight. There is an impact on that, or is there any kind? He told here that he's using the Saliency Map before the gradient descended.
Sorry, I didn't understand now, David.
Well, if it's possible, we can discuss on that before.
No, that's because I'm not hearing too well right now. But if you repeat,
okay.
I think.
Okay. I don't know if you can see here on the StreamYard, Diego Lucio was posted this question at 3 p.m., 3 and 37. 30, yeah, I'm using.
Yeah.
It's a complement of the later question.
Saliency Maps.
Yeah.
Yeah, Saliency Maps have been also increasing a lot their popularity. Honestly, I didn't yet perform any experiments about Saliency Maps, so I know that they attain very good results in providing visual explanations also. But well, I cannot say much more about it.
Okay, thank you. Another question from Professor Eduardo Luz from Federal University of Ouro Preto. Professor Hugo, how about using the attention mechanism for interpretability?
Yeah, same thing as I said before. Attention has augmented the popularity a lot. Hopefully, we will soon do additional experiments using the attention mechanism, which up to now we did not.
Okay, thank you. Okay. Well, Professor Hugo, Renan Oliveira Reis. Does the GAN model behave well for imaging in the wild?
Well, the images we use, they only relatively in the wild. We had not performed any experiments with real in the wild data. Okay, so I suppose that the explanations will be perhaps a bit more blurred. Okay, blur is not the blur of the representations we obtain was not a serious problem, because if we obtain a blurred representation and we will match against another blurred representation, the final result will still be okay. So I suppose that perhaps if we use images in the wild, the most challenging phase will be the first one, segmentation. But if we are able to segment the in the wild data, everything else from that point should work, I believe.
Oh, thank you, Hugo. Thank you, Eduardo, for the question. Not for the question, sorry. Well, another question from Professor Claudio Jungi from Federal University of Rio Grande do Sul. The categories in the semantic segmentation seems intuitive for face periocular images, eyes, eyebrows, glass, etc. But which categories should be used for fingerprint or iris images?
Good question. I only have an answer, I believe, for half of that question. I do not have an idea about what features will be used for fingerprint, okay? But for iris, we are actually performing some preliminary experiments. You have also intuitive features in iris, okay? We can talk about crypts. We can talk about there are 5 different main features inside the iris that can be used, and they are really intuitive for humans. We have pigmentation spots, we have Wolfram nodules, we have contraction models, we have different categories that if someone sees one example of each of those 5 categories in an iris, will easily understand those biological components of the iris. So I would say that perhaps it's the same thing for fingerprint, but well, I know almost nothing about fingerprints, okay. So I don't have idea for fingerprints. For iris, yes, and I think it would be possible to use semantically evident categories for iris.
Okay, in this case, you are talking about near infrared images of iris, okay?
Yeah, near infrared versions, yeah.
Yeah, thank you. Thank you, Claudio. Thank you, Hugo. Well, the next question posted here, but we have time for more questions. Pedro Silva, also a professor from Federal University of Ouro Preto. Professor, if instead of using the loss function you mentioned, if one uses a loss function based on the decidability index, do you think it could work for the periodic biometric verification problem?
I would not say instead of, but I think that we can also use a loss formulation that uses the decidability index. And if we had that term, perhaps we would be simultaneously learning not only a system that explains the decision, but also a system that creates the genuine and imposter decision. Okay, I would not replace the loss functions that we use for the decidability index, but we'll add another one. I'm not sure if we lose too much in the interpretability by adding the recognition loss formulation, but I would say that it might work. And in a single shot, we will be learning not only an interpreter, but a recognizer also. It's a good idea, yes.
Oh, very interesting question, Pedro. Thank you. I have a question. How do you believe we can use this framework for a proposal from iris image spoofing?
For image spoofing. Okay, the idea it would be to explain why a sample is real or not.
Yes.
Yeah. Well, I think that it's the same thing that we talked a few minutes ago for Claudio Jung. If you are able to identify semantically understandable features in real images and in fake images, I think that you are able to apply a proposal or a processing chain similar to this one. Everything starts by the ability of a human to identify semantically evident and consistent features in your data. I'm not completely sure about that specific problem of fakes, but if you are able to classify a fake according to different features understandable by humans, I think yes.
Okay, well, thanks a lot. Do we have more questions? I have some noise here. Well, I love the presentation. I have received another small questions on the WhatsApp. People, we can continue the discussion with Professor Hugo, not Luke, on the Discord channel. And if you want, you can also write Professor Hugo.
Sure.
Okay. Hugo, MCP at
DEUBPT.
Okay. Hugo, thank you very much for your presentation.
Thank you for the invitation. It was a pleasure for me. Thank you. Okay. Thank you, everybody. Thank you, David, in particular. Thank you.
Thank you.
Thank you.
You're welcome.
See you.
Well, let's close this session. Thank you, everybody. I love the presentation. Very interesting. Thank you, everybody. Okay.